Hi, this is recap lecture number 4, and this focuses on different sorts of estimation of area under a curve, basically the idea of a Riemann sum in general, as well as some other ideas that were in chapter 4 of your textbook when we were going through it. You can see in the first little bit of your outline there that I just drew some pictures here to help us remember right hand versus left hand Riemann sums. So something to note about right-hand Riemann sums, the first picture that you see, is that you might be asked questions. I've seen questions lately on released AP material that talks about the estimate of a right-hand versus left-hand rectangle and whether it's an overestimate or an underestimate. I don't think that's something that is worth memorizing per se, because I think with a quick little drawing, you can understand if your rectangles are going over the shape that you're trying to find the area of or under. And so hopefully you can tell or have had enough experience that right-hand rectangles are going to be overestimates, where the function would be increasing, like on this part, and right-hand rectangles are going to underestimate if the function itself is decreasing. That is exactly reversed for left-hand rectangles. In left-hand rectangles, the rectangles pop out over the shape where the shape is a decreasing function, and underestimate where there's an increasing function. Again, I wouldn't bother memorizing that per se. I would just make sure that I could draw myself a picture to confirm what I was thinking. So you should understand how to find the area of those rectangles as an estimate of the integral, and then be, anticipatory of the fact that you might be asked about over versus underestimate. Midpoint rectangles are exactly what they sound like. So if in this graph I was asked to make a midpoint estimate using 4 equal rectangles, what I would do is go to the middle of each interval. So the first interval here is 0 to 1. And then I would go to the midpoint or the middle of that section. I go up from that midpoint. Same thing throughout, up from the middle of each one. And that function value at the midpoint is what would determine the height of the whenever that midpoint hits the function, that determines the height of the rectangle. And I've seen this most frequently in context of table data. So if you had, a table of data and it had, say, x is 0, x is 5, x is 10, and then gave you some function values, and it was clear in the question that 0 to 10 was supposed to be one of the rectangles, the height of that rectangle would be found right here. It would be the function value at 5, with the width of the rectangle being 10. The other kind of estimate that we talked about was a trapezoid estimate, and trapezoids can either be underestimates, like this one would be. I'm really having a hard time drawing with my finger. Or they can be, or actually that would be an overestimate. I take that back. Underestimates would come over here where the shape is concave down. So I just didn't draw something that had enough of a curvature for us to really see. Oh, this is just looking horrible. Okay. Hopefully on your picture with a pencil that's nice and sharp, you can do some more precise drawing. So a trapezoid is going to be a very tight estimate to the curve because those little secant lines kind of hug the curve. And where you have a shape that is concave down, like over here, then your trapezoids will be an underestimate. And if you had a shape that was concave up, like this, then your trapezoids would have an overestimate. Okay, so that's what I was trying to get at before. I'm sorry about that. This whole shape is concave down, so they're all going to be a little bit under. And if you have something that's concave up, you can see that the trapezoid shape itself has too much area for the area under the curve. Okay, so concave down, trapezoid would be an underestimate. Concave up, trapezoid is going to be an overestimate. Again, I've seen the trapezoid most often asked about in the test recently as using table data. And trapezoid rule, as it's called, is actually not as helpful as we would like in the sense that the AP writers have gotten wise to our ways and understand that if you have equal intervals, like say you had 4 trapezoids here, then that makes for a very easy problem that is easily programmed into calculators as a formula. And the AP writers have gotten around that by either giving you a non-calculator question about it or by making the trapezoids unequal. And this would be an example of the kind of table that you might see where you're not actually given the function as a rule or an equation, or even as a graph. You're just given discrete points and then asked to do some sort of estimate with trapezoids. That's the kind of thing that's been more common as of late. So here's a question where I just ask you to do left-hand estimate, right-hand estimate, trapezoid estimate using the intervals that are on the chart. So of course we could just do this as like 2 rectangles and go like that, but that's not really what they mean when they say like using the table. They mean, you know, using each little part like that as its own shape. So that's what's implied. I know it's not exactly what they always write, but that's what they mean. So I'd like you to just pause the video, take a minute, do these 3 estimate questions, and then when you come back, you'll be able to check your work. Okay, thank you for working that problem by yourself. That's how you get the best practice and the most bang for your buck out of your time here. In the table, you see that I've written in red pen 2, 3, 2, 3, and that's to indicate the different widths. So the distance between 0 and 2 is 2 units. The distance between the 2 and the 5 is 3 units. Between 5 and 7 is 2 units, and so on. So those are going to be the widths of our rectangles. And you can see down below here, in the purple line of writing for my left-hand estimate, I underlined in red the widths of the rectangles, and then since it is a left-hand estimate, we would use the function values other than the one way at the end. So this, oh, sorry, not on a pen. So this guy, this guy, this guy, and this guy all end up being heights of rectangles, but not the furthest right endpoint because we're doing a left-hand estimate. And then when we do the right-hand estimate, this is going to be left out. It'll be this, 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 and this that get used. So you can see my work here. Hopefully yours is the same, and the underlined red numbers are the width. And then for the trapezoid estimate, I just did each individual trapezoid because there's only 4 of them. The nice thing is with the AP test writers not asking trapezoid rule questions where the trapezoids are all of equal height or equal delta x, they don't tend to ask ones that have a lot of trapezoids because they know that a lot of folks are going to just write it out the way that I did. Again, the underlined red numbers are my heights of the trapezoids. Okay, so let's go now to mean value theorem for integrals. And the word mean here indicates an average. So a good way to help yourself remember these theorems is to think about why they're named what they are. So the idea of an average that's present in the mean value theorem for derivatives, think about that. Where do you see an average mentioned in that theorem? And that's not what I'm talking about here. So this is the one for derivatives that we reviewed a couple days back. Hopefully you know that that idea that's present is the idea of the slope of the secant line. That's an average rate of change. And so that is, I guess I'll write that too, average rate of change. And so that's the average that's present in the mean value theorem for derivatives. Okay, so the idea of average that's present in the mean value theorem for integrals is similar but different. It is the actual average value of the function over the interval. Average value of f of x or whatever function on some specific interval. Okay, and in the theorem, this is called f of c, and that f of c is the height of a box. Let's call it the special box. And what's special about the box that I'm thinking of is that it's a box that has the same area as the area under the curve from A to B. Okay, so let's see if we can try to write that. Okay, so what I wrote down here is to try to have you represent the idea of the mean value theorem in a nice non-mathy sentence. I'm actually just going to stick with drawing a picture because to me, the picture says everything. Okay, so I actually just paused that so I could draw and struggle in peace with my lack of drawing skills. But what I'm showing you here is a box, and that box is red, and that box has some particular height. I'm not really sure what it is yet. We'll talk about that in a minute. And its width is the distance from A to B. And that red box is the box that has the same area as the area under the curve from A to B. Now, I just kind of estimated this in my drawing, so I hope it's somewhat right to your brain as well. But say you had all that area it's indicated in yellow, and the idea is this box has the same area as that green lumpy lump, or that yellow lump. And that's what the mean value theorem for integrals is all about. It says that there's going to be some spot in here, and we're going to label that spot C. And if you go up from C until you hit the function, and then go across, it's going to be the function value at C. And so that the red box's area is going to be base times height. So the base would be B minus A. Come on, buddy. There you go. B minus A times F of C. That's base times height. And that would have to be equal to the exact area under the curve, which would be the integral from A to B of my function. And if you reorganize that sentence and solve for the f of c component, this part is what is called the average value of the function, this number right here. Okay? So on the next page, there are a couple of problems that I'd like you to try. Again, pause the video and then come back and check your work. Okay, so while I had the video paused and I was doing my writing, it occurred to me that I really meant to talk to you about this too. So I've written in purple the average value of the function f on the closed interval from a to b. That's our definition that comes from the mean value theorem for integrals. But I'd like to just point out, because I've noticed in some of the free response questions lately, we're getting a little confused about average rate of change versus average value. These two things are actually related. This b minus a comes down here, and you notice that when you have this part, you think of that as an antiderivative and plug in the bounds, you get this sort of thing. The part that's written in blue represents what we might call algebra 1 slope formula, right? Or an average rate of change. If you're looking for an average value of a function f, you're doing the slope formula with the antiderivative, okay, is a way to think of it. Now, we don't have you learn it this way because there are times that you don't actually know the equation for the antiderivative, but you do know something like area under the curve. And so this part would make more sense to actually have as our representation. But I thought I would point out that connection in case you guys had not really realized that before. All right, let's check the work that you did while the video was paused. So just take a look at this. Okay, pause the video if you need to, and then there's a little piece at the end that I haven't actually written up yet. We get to the point where we have 2 equals 9 over c cubed, and then we just need to finish that out. So 2c cubed would equal 9, and then c itself would be the cube root of 9/2. And I encourage you to leave things kind of mucky-muck like that. And then the one down below that, I wrote out average value of the function definition, the one that was just on the previous screen, and to derive, plug in the bounds, you get 2 over pi, but it asked us to find the x value at which the average value was attained. So we're searching for what you guys might call the c value or the x coordinate. So we just need to set the original function equal to the average value of 2 over pi, and that would be whatever the inverse cosine of 2 over pi is. And that's something that's going to be an awkward number, so I just left it like that. All right, these last couple questions are actually from our textbook. I just think they're really, really good questions. So the first part here says we've got a graph of function f. We're supposed to evaluate the definite integral from 1 to 7 of this function. So since we don't have equations for this, the intent of this question is not for you to go ahead and find those linear equations. The intent is for you to partition it up and find the area of each little chunk. So think about that. and you would have a trapezoid here, and then maybe you would want to do like a rectangle and a triangle, or a couple more trapezoids, whatever, and then a rectangle. That would be one possibility of a way to partition it, not the only one. Okay, have you figured? I'm kind of talking slow because I'm thinking that you're figuring this out. Are you figuring it out? Okay, I'll have spoiler alert. I'm about to tell you what it is. Should be 8. Okay, so I hope that's what you got. And then if you're asked, I like this question because it fits with what I was just telling you about needing to know this formula or format of the average value. Because here we don't want to actually find the antiderivative and do the slope formula like algebra 1 to find the average value. We want to think about, okay, I need to just do area under the curve for this part and then have 1 over 6. So this is just going to be my previous answer, 8 divided by 6. That's the average value that this function attains during the interval from 1 to 7. The most classic student mistake on average value is to average the endpoint value. So just say, oh, well, it's 3 here. The function is 3 here, and the function is 1 down here, and the average of 1 and 3 is 2. That is incorrect because it does not take into account the fact that this function spends a lot more time, if you will. It has a lot more places where the function value is 1, for instance, as compared to those higher values. So it makes a lot of sense if you think about this, because what you're doing is you're adding up something and then you're dividing by the x. Doesn't that sound kind of like an average to you guys? Like adding up all these y's and then dividing by x's? I hope that makes sense to you as a way to take an average. All right, and the next part asks, and this is the part I really, really like about this question. The next part asks, what happens if the graph goes up to? And there are a couple ways you could think of this. One way would be to literally think about sliding this graph up. And then what you're going to accomplish is gaining a little rectangle of space underneath that graph. And that rectangle would be 6 units wide and 2 units tall. So you're going to add 12 units of area. And so what that means is my answer for part C here is going to be 8 plus 12 for 20, and 8 over 6 plus 12 for, I guess that's 20 over 6, right? Is that right? I think so. Okay, so would be one possibility, okay? Another possibility would be to think of actually adding to this integrand, having a plus 2 in here. But the end result would be the same. All right, the last little part, I again would like you to pause the video and try these. Understand that when you have absolute value involved, that's going to flip part of the region that is below the x-axis, so it's above the x-axis. Otherwise, you're going to think of that little blob of A as being negative. Okay, so I hope you tried all those on your own. Remember that when you have area under a curve, you are involving signed area. And so when you have this total given to you, the 3.5, that should have told us that lump B was a positive 5 area, and this little guy A has negative 1.5 as its area. So those are the first 2 answers, and then the rest of them, just use those in combination with each other. Should you have any questions, please write them down on your notes now so you remember to ask me tomorrow. And thanks for watching this and reviewing your Chapter 4 material.